No. Did you make cafe out of hairstyle?
No, not yet. I've seen him around, but
yeah.
I will love to meet him.
Yes.
Well, I spoke to him yesterday. Yeah. I don't know if you know. Yes. Yeah. I haven't seen him for a while. Yeah.
Good. So you're collaborating, I guess.
Yeah. Also with Ricardo, you know everyone. Yes. Also on this topic. I guess we have some collaboration. Yeah. How did you go? Yeah, a couple of times. That's come on.
Okay.
That's great. The goal is to give an overview of one week.
Yeah, sure.
I think that's the topic. I think we'll work. Yeah. So where are you based? I'm in Topology. Oh, okay. I don't think that.
Let's see.
I think that stuff there for Thanks, Marcelo. Hey, Mr. That's a good director.
How are you doing?
Yeah. I'm gonna get some water.
Yes.
Noise.
Maybe. So should we open?
You've been there for a while. Yeah, I've been there for several 8 years. So I like it, yeah. Right now it's in the dark and gloomy, but here is nicer right now.
Yes.
Well, you can get like dark. Yeah. No. Yeah. Bio. Why? So I need this here. What is it? We can't talk. Right.
Running, so very much.
Here is okay.
Oh, okay.
Okay. Because it was recently. No coffee. What do you want to say?
Yeah. Yes. My path. Y eso ya pues normal, se puede.
Sí, muchas gracias.
Sí, no, no, pues está, porque se tenía que haber
También la guardería. Claro, un poco lo que vamos a hacer. Sí, o sea, la idea es un poco dar ahí. Digamos. O sea, bueno, al final, ya luego al final a lo mejor sí hay más detalle. Tenemos que más o menos la idea de claro. Sí, sí,
No sé cómo se hace.
sí, además es algo que o sea, normalmente los teóricos está claro, más que a veces como pueden preguntar en plan, si vas a repetir todo, pues no vas. Pero la verdad es que hay sorpresas y luego, sobre todo, experimentales. Sí que me encuentro muchos que menos mal que ¿sabes? Sí, porque muchas veces crecen cosas amorfas y no las usan o simplemente, por ejemplo, tenemos un proyecto con que un montón de pasos de producción tienen materiales amorfos y que les gustaría integrar, o sea, si en algún momento algún material topológico resulta ser eficiente, es mucho más fácil hacerlo amorfo y integrarlo que tener realmente una fabricación ahí que ahí sí que hay sí, sí. Son la gente que hace transporte, ¿sabes? Transporte. Es un experimental de transporte. Estaban haciendo una cosa interesante, es cuando haces nanowires cada vez más pequeños, si haces copies cobre, lo haces cada vez más fino, la resistencia pero cuando tienes un material topológico, satura porque tiene estados de borde y a un momento o sea, ya estuve, ¿no? Lo hace mucho. Entonces, y esos nanowires muchas veces los crecen a amorfos y han hecho ya materiales amorfos topológicos. Que son, bueno, lo que ven es que la resistencia no satura tan mal como el cobre, pero no saben por qué. Entonces, hay como ese interés de desarrollar un poco una teoría detrás y que se repita por si serán los estados topológicos, pero no hay herramientas.
Eso no hay ninguna otra alternativa. O sea,
sí, sí, sí. Sí.
Siempre hemos tenido cambios,
Ya.
Pues complejo.
Ah, no.
No quiero
Sí, a ver, pero eso ya te la fe.
Let me introduce, sorry to interrupt, my code because it is called.
Sí, sí, sabe que los primeros que hizo desarrollamientos para cancelar estos medios topológicos en espacio real para sistemas de solución. Está muy bien. Sí, también.
You know, Timo told me I have to speak with you.
Oh, really?
Yeah,
I remember asking him. Yes, he came to Grenoble.
He made the breakthrough right now. Physical letters a couple of months ago.
Okay.
You know that?
No, I don't. Okay. I would love to hear
I will display that.
Yeah, okay.
So we can see those in the months.
Yeah. You come here often.
Yeah, so I was telling him that you are a regular visitor of
Yes.
every
I
year.
sit here because my eyesight is not very good. If there is a small formula, I prefer to be.
Today's gonna be a
I
lot
got the two cataract, what is English cataract,
yeah.
and one of two did not went well, so my eyesight.
But recently?
Yes, in the first half of this year.
Okay.
I have a pretty big pictures. So I have like all my slides. I have like one big picture, and mostly well, depends on
Yeah.
the size. I hope.
Now, but the formula, sometimes there are slides with the reference very small, formula very small.
Yeah. Those I have here.
Cluttered, there are sometimes cluttered slides.
Well, you told me if at the end you can tell me if
Yeah.
if I need something.
Pues igual quitamos, ¿te parece?
Sí.
Cierro la puerta. Okay, so good morning, everyone. So it's a pleasure to introduce Adolfo Grushin. Adolfo has been in San Sebastian several times before that, but this is a special occasion because I think this is the very first seminar that he's delivering here as a Ikerbasque research professor at the IPC. So he has, fortunately for us, he has decided to join the IPC. He started his position in July the 1st. He's still located, his office is still located in the Corta building because we, as you know, and I hope that we don't listen, but we have some constructions going on. So he will be later on installed in the new building, but up to this moment, so he's still in the Corta building. So Adolfo, he made his PhD in the Autónoma University in Madrid. After that, he went to several places. He was in Dresden as a postdoctoral researcher. He also went to Berkeley, where he was a Marie Curie fellow, I think, right? And then he obtained a permanent position in Grenoble, in the Institut NL, right?
That's right.
Until now, until the 1st of July. So thank you very much, Adolfo, for the seminar, for joining the IPC, and we are looking forward to your presentation.
Thank you very much for the introduction, and thank you for coming. Ni Adolfo Grushin, nice. I'm learning Basque, but this seminar won't be Basque yet. Maybe the next one. So yeah, I'm gonna try to give a little bit of an overview since we're new, and there are like some new faces around in my group that you might have seen in the coffee. I'm going to try to give a little bit of a high-level overview of what we do, and then at the end, maybe I'll go more technical and maybe give you some more meat. But hopefully, if there's anything unclear, just let me know and I'll stop. I don't have to get to the end. So what we do is, we treat systems a little bit like this. You have no translations, something that is maybe very disordered, maybe not, maybe some things are disordered, but there's some structure to it. And we try to ask questions like, what's the topology and what's the wave function geometry of these things. So let me start off by explaining why we should care about this. So most of you, I think it's safe to assume that do crystals. They are very nice because they're very symmetric, and this simplifies our lives. But somehow there's also a lot of solids that shouldn't be left out. They're still solids. And if we're solid state physicists, as I am, there's no good reason to ignore them. And you might have, once you try to imagine what these things are, you might think of amorphous solids that are completely disordered. How do we even start thinking about these? Or maybe you have experience on working, just starting with a crystal and maybe disordering it a little bit as a perturbation. But of course, there's a whole range of systems that go in between these two limits. There are alloys where you kind of substitute different atoms by others a little bit randomly. Or you have Moiré structures, which are not technically periodic. So you just stack two layers of, let's say, 2D materials, and you rotate them with a certain angle. And you don't necessarily have to have a periodic structure. You have quasicrystals, which have been around already for decades. And also as theorists, we like to think also about more exotic things like hyperbolic lattices and fractals that can be done or designed as metamaterials sometimes. So all these things exist in some way or another, but disorder is a little annoying and a little hard. I actually used to hate it in my PhD, but things change. So why bother? So one very simple reason is that actually there are many materials that are non-crystalline. In fact, I could argue that there are more materials that are non-crystalline that are crystals. So mostly because you can make most of the crystals grow in a, let's say, bad way, and so you can create some sort of amorphous solid out of them. So at least are as large as crystals. They have been kind of useful in technology. I don't know. I mean, I always make this joke, but there's some subset of ages that have used this object, which is the calculator, and this solar cell here is made out of amorphous silicon. And so it's nice because it's you can afford a calculator because you're making it with cheap growth methods, and one of them if you grow very clean silicon, it's very expensive, but if you go amorphous silicon, it kind of reduces the costs. So amorphous materials are used not only as solar cells but also as mirrors for their lower thermal noise, and also in qubits, which is a little bit contradictory. Maybe if you're used to the field because you want to reduce noise and things like this, but turns out to enhance kinetic inductance, which is one of the things that superconducting qubits want to have. You actually need disordered superconductors to enhance this. Maybe you've also used a DVD. So if you use the DVD, you actually inadvertently or maybe knowingly have turned a crystal into an amorphous material very fast. And in this way, you have read what's stored in it. And now you can start imagining things that you couldn't do before only with crystals or only with amorphous systems, which is, for example, turning something that is trivial or uninteresting into something topological, like just by switching the geometric, the structure of the atoms. So it's something we played around. I won't mention it, but just to spark the imagination. So, once you start allowing you to think about these new systems, you want to kind of find interesting properties, not only study them because they exist. So we know, and this has come from the IPC among other places, but a good chunk of this work was done here. We know that many materials are topological. Mostly, if you look at the Fermi level, 50% of them is the prediction. Now, how about these non-crystalline solids? I should mention that for those of you that maybe don't work on the field, like a topological insulator, broadly speaking, is something that is an insulator in the bulk and conducts on the edges. It could be two-dimensional, like the one on the top. It could be three-dimensional, something that is kind of like, I think it was Charlie King that said it's a very frustrating gift. So if you have an insulator here and you cut it, you have a topological insulator and you cut it in two, you get two topological insulators. You don't get to see the interior. It's again surrounded. So this is a little misleading of a picture. And also there are other materials that we call higher order topological insulators, where you have an insulator in bulk, an insulated surface, and maybe something conducting along the hinges where the faces meet. So one thing that we like to ask is, can you find new topological phases, not just redo what we know from crystals? Can you find new materials? What are the experimental signatures? And also, how do we theoretically diagnose them? So mostly we work on this. How do we understand theoretically the existence of topology in non-crystalline systems? Because I should say that, strictly speaking, many types of topology that we know from crystals don't require materials to be crystalline. And it's really an experimental reality. I was already mentioning twisted bilayer or Moiré heterostructure. They have been observed there. You can observe topological phases like on Anomalous Hall. In quasicrystals, people have created photonic crystals where they shine light and they see that it can propagate around the edges, and they attribute this to topological properties. Even in amorphous systems, so this is a video of a system of coupled oscillators. In reality, they're gyroscopes with a little magnet, and you can excite them. They're coupled harmonically. And if you excite on the boundary, you'll see this kind of edge mode going around with little perturbation in the bulk. And if you look at the structure, there's some hexagons, but there are also some like larger plaquettes that are not hexagonal. So it's a disordered system, yet it shows edge states. In solids, I collaborated with some experimentalists to study amorphous bismuth selenide. So bismuth selenide as a crystal is a topological insulator, and Frances Hellman and her group grew amorphous bismuth selenide, and Alessandra Alzar and her group did ARPES, and you can see that it's not a mess as you would expect maybe for a very disordered system. It actually shows kind of dispersive features, and it shows like repetition. So there's some order to this data that we associated with a topological surface data. So I'm not going to go into the details, but I'm happy to talk about it if you have questions. But this just motivates the fact that we have amorphous systems. They can be topological. So how do we actually go about understanding them? A little bit more of a motivation, which is a little bit what I am kind of currently doing with my group. These non-crystalline materials notably include superconductors. And so you can have disordered superconductors that have a reasonably decent critical temperature. I'll give some examples in a second. But superconductors have been found in amorphous materials, in granular materials, and quasicrystalline materials. So we should also try to understand what's going on there. And to motivate this question, I am going to list here a few materials: bismuth, beryllium, gallium. They're crystalline TC and they're amorphous TC, superconducting TC. And you see that, for example, bismuth has a huge enhancement just by becoming amorphous. So it's really several orders of magnitude better as a superconductor. Now, this is typically attributed to a higher density of states in the amorphous system. But it's still interesting to ask what, and this is a very old question, admittedly, how does disorder help materials become a superconductor? Can topological superconductors exist? Because you may be aware that if you have just a normal S-wave superconductor, there's the so-called Anderson's theorem that tells you that a superconductor should be robust to a moderate amount of disorder. This is not the case of topological superconductors or unconventional superconductors, but yet there are examples in the literature where this is not exactly true or is very nuanced. So we want to explore a little bit that. And also, you might have interacting topological states, typically called topological order states, like the fractional quantum Hall effect is a stereotypical example, which might require or might show new phenomenology with in disordered systems. So this is something I'll touch at the end. So all these questions are interesting to us, and you might say, okay, this we have been studying for ages. So what's new? So one thing that I think it's been a little bit underexplored is something that it's been called, or I call, a structural disorder. So normally you would think of disorder as essentially in a crystal, you can disorder the bonds, let's say randomize the bonds, or disorder the on-site energies of electrons living at different sites. And this is kind of a typical Anderson problem. But there's, as a theorist and even an experiment, you can think of a different kind of order that has no disorder in the energies, or a different kind of disorder that has no disorder in the energy scales. It's just a connectivity disorder. So here you see it's kind of like graphene. It has, every atom has 3 neighbors, but it has plaquettes that are not hexagonal. So all the hoppings and all the on-site energies are the same. So there's no disorder there. But there's certainly effects on the electronics propagation because of these defects. And so usually when people have model amorphous materials, they have still concentrated on let's say, on these, on the left side, but not so much argued what is the difference or whether there's a difference of these, this structural disorder. And so in amorphous materials, you will find all types of disorder, but as a theorist, we have the luxury of separating them. And so perhaps we can find new phenomenology and motivated experimentalists to try and look for that. And to motivate it a little bit more experimentally is actually, it's having a controllable knob. So this is a paper from 2023 that they grew amorphous graphene with different degrees of structural disorder. So from left to right, you see more and more pentagons and heptagons and other types of defects, and the conductivity properties change, of course. And I think there's more and more groups that are capable of growing, for example, 2D materials that are disordered, which is something that I think also has been a little bit underexplored. So this is a little bit of a motivation. And specifically, what we like to understand is how wave function topology and geometry affects the electronic properties of these materials, and maybe revisit some of the known explanations of, let's say, diverse superconductivity or interacting systems under this kind of new language, and hopefully bring something new to the game. So I'm going to introduce the group because this is the most important slide. These are the people that you will see around. So Justin and Laura are still in Grenoble and they will stay there. Justin is about to graduate, so if you have a postdoc and you like what you see, let me know. And Laura will be visiting soon. But the ones that you will see more often are the ones in yellow: Sergi, Isidora, Peru, Hector, and Adam. And as you see, Adam is very excited to figure out what's going on. So we use all kinds of methods, as you see. So let me start with topology, maybe a little bit of an introduction. So I apologize for those of you that know this, but I hope I take an angle that is a little different. So my angle is going to be, I'm not going to talk about momentum space or donuts. That's sort of the other. So, but just bear with me. It's a little maybe different than your usual introduction, hopefully. So I'm going to build a trivial insulator first. I'm going to take two orbitals, let's say S and P. I'm going to build the most boring thing you can imagine. I'm just going to put them in a crystalline lattice, square lattice, just at every site. So if you plot the bands, so the well, first of all, these I shouldn't say, but let me emphasize that these states are very localized. They're like they're in the orbital. I'm going to ignore for most of this talk the shape of the orbital, but let's say they're there, localized. They don't talk to each other, no hopping. And so maybe it's a little small to see, but if they're localized there, the position operator commutes with the Hamiltonian. So I can find an eigenstate that is both localized in position and has a well-defined energy. That's my definition of a trivial insulator. If you go to momentum, you will see that nothing really disperses. So energy versus momentum, you have two states, S and P orbitals, nothing really very interesting, but there's a gap. And if you now add a little hopping, now you'll blur this picture a little bit. Bands will disperse, so electrons will acquire some group velocity, and so on. And you will, as we learn, we will form block states. But you can kind of rearrange these block states of all this. Let's say, imagine this band is fully occupied. You can kind of rearrange them again into some convenient basis. Where electrons again are kind of localized around sites, and we know that this should be possible, or we think it should be possible because we have a gap. So it's an insulator. You have to pay a certain energy to make electrons conduct, and so they have to be kind of localized. And in this case, the binary states have these oscillations, so there's superposition of block states. So it might be not exactly like orbitals, and so as such. The position and Hamiltonian operator would typically not commute. However, if I can go from my trivial atomic insulator to this trivial insulator, so this trivial atomic limit to this one without closing the gap, or if I'm also respecting the symmetries, then I'm going to say that they're in the same topological class. If I cannot do that, meaning if some direction remains delocalized, this will not be allowed, and I will have to close the gap in the process. And so these belong to different topological classes. And so what I'm saying is that, give me a Hamiltonian, it might not commute with the position operator that you choose, but it might be possible to deform these two operators to commute. And if I can do it, it will be trivial. If I cannot do it, it will be topological. And immediately, just from this kind of picture, you can see why topological materials have to have edge states or surface states. It's very simple. You have something in the middle that in the bulk that doesn't commute with the position operator and it cannot be deformed to commute. You have something outside that let me define the vacuum as a trivial insulator. I don't know, think of argon here, or like, I don't know, oxygen. The electrons are sitting there at the molecules. So let's say that's Hamiltonian position operator commuting, and in between there has to be a gap closing because of what I just said. So, and that gap closing defines the surface of this material, and it's gapless, so it's a gapless surface. Now, in 2D, and this is where I'm going to live for most of my talk, it's the same idea. You have a bulk that is insulating, a side that is insulating, and somewhere in between you have an edge state. So that's the famous, for example, that's the case of the quantum Hall state, where you have some transverse conductivity that is quantized in units of E squared over H. So C is an integer times E squared over H. So let's see, how do we understand topology or calculate this integer using this kind of a non-commutativity. So mathematicians have been kind of quite prolific at finding how you can deform operators to commute. And so this is something that I'm going to use here. There's an operator, and this is maybe a little technical, but just bear with me for a second. So there's an operator that kind of measures whether I can commute two operators, can deform two operators to commute. This is called the spectral localizer. So something that we use a lot. And let me just tell you, you don't have to like really understand what's going on, but just let me tell you, this is an operator, should have a hat, that takes the Hamiltonian and the position operators and has the following property. So you give me Hamiltonian, you give me position operators, and what happens, I diagonalize this operator. So I look at the spectrum, not its eigenstates. And what you will find is that if these two Hamiltonians, let's say, are different in different topological classes, the localizer spectrum necessarily has a gap closing. And this has to do with how X and H commute. So this, if you want, it's a theorem. And what's nice about this approach is that, first of all, you look at the spectrum of an operator. So you don't need eigenvalues. You don't need eigenstates. And second of all, it gives you also a sense of robustness of this phase. So there's a gap. This stays, given the Hamiltonian gap, this localizer will also be gapped. And the size of this gap gives you the size of the perturbation you have to add to move one state across zero. And then, depending on the topological insulator you're dealing with, you have to ask different things to calculate the invariant, the thing that characterizes the phase to this operator. So in particular, if you want to calculate this Chern number or this Hall conductivity, it would be then the difference between positive and negative eigenvalues of this operator. Or if you want to calculate a Z2 index, it will be some sign of the determinant of this spectral localizer. So the localizer is, let's say, always the same operator, but the question you ask to calculate an invariant might change depending on the symmetry class of your system. So this, I will refer to this difference between positive and negative eigenvalues as the signature. And that I will show later how that determines the Chern number. Okay, so you might know another way of calculating this, which is just you take the integral over a quantity called the Berry curvature over the Brillouin zone in a crystal. If you have a crystal, you might be familiar with this expression. That's how you would calculate the Hall conductivity of a occupied band. But actually, you can do something that Rafaele here did, which is essentially to Fourier transform this expression and write it in real space. And so what this allows you to do is, just by this simple, like kind of very nice idea, you can write this trace or this integral over the Brillouin zone, instead of as an integral of the Brillouin zone, you can now trade it by a sum over real space positions. So you can define what we call a local Chern marker, where if you calculate it for every site, and then you kind of average it out over an area, and this will give you the Chern number. So if you have a finite system, it will be mostly quantized in the bulk, in this case to -1, and then because it's written as a commutator, it has to vanish overall. So then the edges will give you some opposite sign contribution that kind of cancels everything out. And what's nice about it is that, as I was saying, this is the bulk average over this local Chern marker, which has been used a lot, and I think it's very useful. Gives you a Chern number, and it's essentially the localizer signature as well. So this is something that was implicitly kind kind of mentioned by Loring, who introduced the localizer. But we recently showed with Jens, who was visiting actually this couple of weeks, and his postdoc Grushin, that you can kind of connect the two, which is kind of nice. Okay, so as far as diagnostics goes, you have a, let's say I give you a system. You can look at whether you have edge states. You can look at the local markers or transport. Turns out you can also use, if you have local symmetries or average symmetries, you can also use those to characterize topology. This is something we've been doing as well. Or if you're more kind of first principle like, or you like more first principles, there's also other ways that, kind of a meaningful way of comparing systems that are crystalline and amorphous, for example, and comparing their projectors to the occupied states and coming up with a quantity that could tell you it's maybe not as reliable as all the rest, but it's nice because it works for DFT calculations. That also tells you whether you have a topological state. So these are kind of the three main categories. This last thing was done by Danny Miuño, who was a student with me and Fernando here. So these are kind of the most kind of the three broad ways of how we characterize topology in real space. Now there's another aspect which is that's been like discussed a lot recently with flat band systems in particular, which is the wave function geometry. So let me introduce that. So remember we had this very boring insulator. If I now, there's no hopping. If I now ask you, okay, how similar are these two wave functions if I move a little bit in momentum space? The answer is probably that they're essentially the same wave function, possibly up to a phase. And so if I characterize or I parameterize my wave function with an angle, it's not always possible, but it's nice to draw. Or it's not always as clear as this. Then you would say that they're basically the same as up to a global phase. Now, if I start now fiddling with the bands and adding hoppings, then they might become a little different. And so it's possible to come up with a measure of how different these wave functions, these neighboring wave functions are, and that's exactly what people call the quantum metric, which essentially you calculate an overlap between neighboring states, or you change a parameter here, momentum, and you expand in small deviations, and you find that you define this metric G. So why is this useful? So here this is just the same as before. What's interesting about this is that this metric kind of tells you a little bit about how spread the wave functions are. These Vanier states that I was talking about, the trace of this object gives you essentially the spread. And so if you have a very large spread, you think of the states more as metallic. If you're there localized or this spread is of the order of the lattice spacing, then it's more like localized or an insulator. So I have introduced basically two quantities, the metric and the Berry curvature, which I didn't write like this, but then let's write it like this for convenience in a second. So the curvature, technically speaking, is some phase difference between wave functions. So it's like a little bit the imaginary part of some object. As we saw, maybe I was a little too quick, but I defined the local term marker. So this is again the same thing. And it's the imaginary part of some real space quantity, which is what I was plotting before in blue and red. The metric, on the other hand, is the distance between states, so how different two states are. And it tells you the spread of the wave function. And it too can also be written as some marker, so it's some real space object. And what's neat about these two expressions is that you kind of can combine them into just one single quantum, what's called the quantum geometric tensor, whose real part is a metric and imaginary part is a Berry curvature. So if you now trace the curvature over real space or momentum space, you'll get a topological invariant, and on the metric, the trace of the metric gives you the spread of the Vanier states. So it gives you a sense of whether you're dealing with metals or insulators. And why is the metric important? Well, it kind of allows us to rationalize a little bit the fact that flat bands can superconduct. So if you have a flat band, as in my trivial insulator, electrons were localized. So if you form Cooper pairs, how can they propagate? How can they even carry supercurrent? So one way is if the band it actually has some, if the Van der states have some spread, then these Cooper pairs can overlap and can carry supercurrent. And so this kind of allows us to understand a little bit why, for example, twisted bilayer graphene that has a flat band can still superconduct, because the superfluid stiffness, namely how easy you can carry a supercurrent, has two terms. One comes from the dispersion of the bands. If you have very dispersive bands, you can also carry supercurrent. But if you turn this dispersion to zero, there's still a term that remains that is related to this metric that I was just defining. So there's a geometric contribution to this equation. Okay, and I'm gonna end my introduction with a kind of work by Ivo and then followed by many others, which I think it's a really beautiful inequality that kind of connects the two things. So I was telling you that if I have an insulator, my trace of the metric or the spread of these linear functions is essentially of the order of a lattice spacing, or it can be smaller. However, if you have a topological state, I told you that position and Hamiltonian operators don't commute, and this turns out it implies that there's a limit of how localized the wave functions can be. And so there's a very nice inequality that relates these two. So if you have a system, a 2D system with a Chern number, or naming some whole system that has a finite Hall conductivity, the trace of the metric is always larger than the Chern number. So that tells you that if you have a Chern number, you cannot squeeze the wave functions smaller than a unit cell, essentially. Just kind of a neat result that relates to the two. And this work has been very influential to understand modern materials. Okay, so questions so far. I'm gonna now give an example of this, maybe more pretty pictures. And so this might be a little. So this is a very simple example that we did with Hector and Justin. So Hector is somewhere in the room, which is it's a way of showing how these things work in practice. And just to light up a little bit the mood, I don't know if you follow this. I guess you have heard a little bit about it. There was a breakthrough in mathematics a few years ago by an amateur mathematician, actually a retired print technician, if I remember correctly, who was, he was interested in tilings, and he discovered a shape that could tile the plane aperiodically. So normally, if you have seen the Penrose tiling, for example, you need two types of polygons to tile the plane without holes. So there was an open problem in mathematics whether you could do that with a single shape. And this person, David Smith, found not only this, but found a whole family of shapes that could do this. And so I'm going to show you a video of this in a second. So these are the family of shapes. I'll tell you a little bit what's changing in a second, but you see there are no holes, and that's kind of how you go from different from members of the family. So how do we do this? Basically, the tile that he discovered was what's called the hat, and by changing the relative lengths of the side of the sides, so let's call one length L, and there are only two types of lengths, L or 1 minus L. You can go from L from 0 to 1. You can go through this family of shapes that all tile the plane aperiodically, meaning there's no Brian zone, or it's more like a quasicrystal if you want. And so one thing that we typically do, like the way we model amorphous systems and quasicrystals, is we take a system like this, and we say, okay, let's put some hoppings that are interesting to us. For example, hoppings that would depend on the angle or the relative distance between sites, and maybe some on-site terms, and see what happens. In this case, we wanted to see what happens as you move from one member to the family to the other, whether we could tune topological properties or tune geometrical properties. So it's like a toy example of how you can tune things. So we chose for that, we chose a model that has a Chern invariant, so meaning that it has a Hall conductivity. If you put it in a crystalline square lattice, it'll give you a Hall effect. But the question is whether this will happen here as well. So if I would choose the sites to be exactly on a square lattice, it'll give me a Hall effect. If not, this is what we are going to find out. So how do we characterize topology? Now, you're no momentum, no periodicity, but no problem because we already know how to do it. So I'm going to show you a video of how the spectral function looks as we tune the time. So the size of the dots are going to change, but this is because I couldn't figure out in quant how to change the size of the dots. But maybe explain knows. But this is how it evolves. So as you tune between different sites, you see there's some kind of gaps opening, but maybe some spectral weight inside the gaps. So they're not totally again. So you start with very localized kind of flat bands, and this start dispersing, and they leave behind some states in the gaps. So we want to understand what are these states, are they topological, what is going on. So if you plot the density of states as a function of this parameter L, you'll see that you start indeed with like relatively flattish bands at the most energies, and then you enter these kind of gaps which have low density of states but not vanishing, and then again go to something that is essentially have hard gaps. And so if you look at the spectral function, this is what I was saying. If you look at two cuts, one will have, let's say, if you look at, for example, this gap, this is a hard, like black gap. Well, here you have like little spectral features. So if you place yourself there and you look at the local Chern marker that Ricardo introduced, you'll see that it indeed is quantized to 1 in the bulk, and it's very large and negative and at the edge. So this looks like a topological phase. So this is what confirms the topological phase. Then you can compute the localizer signature because it's actually quite efficient to do so. As I was saying, there are many numerical methods you can calculate this very efficiently. So you can map the phase diagram. You get two phases. Nothing surprising here. These are the same phases you get in the square lattice. You can calculate the localizer gap. So there's something that really close. So there's a quantity that closes and reopens without bands, let's say. And what's nice is that these lines, these dashed lines, indicate the transition of the regular lattice model, like the square lattice model. So just by putting it on this lattice, we have essentially started with something that has the boundaries of the crystal, but then kind of expanded the topological phase. So this is something that was kind of interesting to us, but just as an example of what you can find using these methods. So you can also add normal Anderson, or normal on-site Anderson disorder. You'll find, again, also topological phase transitions. You can start from a trivial state, and by adding disorder, you can go into topological state and again go to a trivial state, or you can tune as a finite disorder, you can tune from in and out of the topological phase. So these are all questions that we can answer in these type of systems. If you plot the average of the metric or the trace of the metric in the bulk compared to the Chern number, you'll see that it's small and growing as you tune L. Then it has a peak. So there's the gap closing. It turns topological because the Chern number is quantized to 1. And then the metric kind of plateaus, doesn't really saturate the inequality. And then it grows again. So we can kind of interpret these as a trivial state, a Chern insulator state, or a trivial insulator state, a Chern insulator, and the metal. And if you look at the maps of the local quantum metric and the local Chern marker, you can also see the same physics. So here in the trivial case, the local marker is basically random, but the local metric is very localized. So if you calculate the trace, you'll get something small. In the Chern insulator case, it's very homogeneous. And in the metallic case, is the local quantum metric is very extended, and the Chern marker is also a little bit random. So that's how you can see it in real space. So this perhaps maybe I should check the time. Yeah. Okay. So this is perhaps a little bit of a let's say, toy example of what we do. We typically have more realistic models and so on, but I thought this was a good place to kind of showcase a little bit what types of tools we use. And now I'm gonna tell you a little bit about how interactions can change the picture. So currently what we're doing, most of my group is working on superconductivity. I don't have results for that yet, but we have very encouraging results. But I will focus on interactions. So just can you get, in particular, fractional versions of these topological phases, fractionalized versions of these topological phases in disordered systems? So what I mean by this is that it's known since the 80s that you can have states in two-dimensional electron gases where you have a fractionalized Hall conductivity with exotic excitations, anyons, that typically, if you have disorder, you will kill eventually. So can you actually use disorder in a way that helps you or gives you some at least new phenomenology? So we know that this is possible because, examples of topological order with anyons in disordered systems exist. So you can there's no problem to make a Tori code if you know what that is, but it has just, for this purpose of this talk, is just a model that has anyons. You can make it disordered, there's no problem. Fractional translators have been seen in more anisotropy structures. Again, I insist that there's no Briand zone technically. It's an approximation for arbitrary angles, but they have been seen in more structures and other systems. And also, people have studied trial wave functions in quasicrystals. So you can take wave functions that are of a fractional quantum Hall state and kind of put them in a quasicrystal and see whether you still get the right anyons. And this has been pioneered, I think, by the group of Van Nielsen. So we know that non-crystalline fractional translators should be able to exist, but the question is, can we do better a little bit in finding them? Do we have new phenomenology or just copies of the things that we see in crystals? And also, can we solve these models? Because once you add interactions, things become very, very complicated unless you do, maybe mean field. But these fractional translators you cannot get from mean field. So the first thing I'm going to say is that we've been working with Alejandro and other people in Harvard and Yale, in Grenoble, and that to use markers that I was discussing before, like the quantum metric and so on, to characterize regions of phase space in your models where these fractional translators can emerge in disordered systems. So there are three indicators. Let's say you give me a model and you can test for three different things. One is what people usually care about are flat bands that have a Chern number. Why? Because if you have a flat band with a Chern number, it looks a lot like a Landau level. So then if you add interactions and you partially fill this band, you might be in the situation that resembles a lot the starting point of where you get the fractional translator case. There's also a case to be made about small Berry curvature fluctuations. So if you take a Landau level and you compute the Berry curvature, it will be homogeneous. But if you take a lattice model, like any translator model, you'll see that it has fluctuations. And minimizing this has been numerically, there's at least some numerical evidence saying that it helps you stabilize fractional translator states. It's not, I wouldn't say is completely understood or when this happens, but this is some numerical observation if you want. And there's also a quantity that is called the ideal trace condition, which, if you look back to the inequality I was showing before of vivo, it's basically saturating this inequality where the trace of the metric is equal to the Chern number. So if you achieve that, these bands that achieve that are called vortexable, and you can show that Laughlin states are exact solutions of that. So that's also a quantity to be minimized. So you want to minimize the bandwidth, minimize the Berry curvature fluctuations, and the difference between the trace of the metric and the Berry curvature. So those are typically calculated in momentum space. So now you're experts on things in real space. So this I won't go through, but basically using the same ideas, you can kind of write down all the same for without using momentum. The only maybe shaky one is the band flatness, because you might have in-gap states. So you might want to use the mobility gap, but turns out this quantity is also useful if you have some well-defined crystalline limit. Anyway, I can go into that if you're interested, but nonetheless, you can write them in real space and compute them for your favorite model. And so this is one thing that we did. You take, again, a Chern insulator model with hoppings that depend on angles and positions and whatnot, and you can calculate the local Chern marker, but you can also calculate this local vortexability, which is nothing but the metric minus the Chern marker. And you'll see that is actually very small in the bulk, which is kind of what you would want for a state to realize the fractional Chern insulator state. And so you can now add disorder in some way and some model parameter that then changes you from Chern 1 to Chern -1 and compute all these quantities and maybe choose a point in their phase diagram that is kind of favorable to realize this. And so part of what these young minds are doing is doing the numerics on this and try to find actually the state. Okay, so maybe in the last 2 minutes, yeah, I will say, I think a very cool model. I will just mention it. I won't explain it, but it's just in case someone is interested in talking to us about it. I think it's a really cool result and a very non-trivial, and maybe we can discuss about it, which was done essentially by Peru and Justin. They came up with this solution, and we also had Charles to help us with the fractonic side of the problem. So the problem was the following: can you find an exactly solvable model that gives you a fractional quantum Hall effect that is disordered? So that's already, I think, a little challenging as a question. But turns out there's a kind of very neat way of finding a fractional Chern insulator, a fractional quantum Hall without numerics, which is the following. You take wires, so just literally 1D wires, and you place them in real space. And now you add a magnetic field. So each wire has a parabolic dispersion. And the magnetic field, what it does, it gives them a shift in momentum space. And this shift depends on the position of each wire. So the band structure will look something like this. So if you wouldn't have couplings between the wires, you'll just get parabolas that are shifted by the amount determined by the magnetic field. And so if you place yourself, so now if you add coupling, this parabolas will gap out where they meet because they can talk. There's nothing protecting that band crossing. And now if you park yourself at the gap, you'll see that there's one state remaining at the edge, because remember that now this is momentum, but it's linked to position. So this is the edge of the system. So it means that you have a chiral edge state. So that's an integer quantum Hall just there. But what Charlie Kane showed in a pretty nice paper is that if you park yourself at a third filling, for example, then you can bosonize this wire. You can use a technique called bosonization to solve this problem, and you can find a fractional quantum Hall state. What we try to do, possibly a little bit naively at the beginning, was imagine these wires are not evenly spaced. If they're not evenly spaced, these parabolas don't meet exactly at the same energy. So they will look more or less like this. And the question is, can you solve this problem still? And do you have a fractional quantum Hall state? And it turns out that's the miracle that Justin and Peru pulled off. You can still solve it. You just have to find when, where, or how. And so it turns out that you can still think of it as coupled wires, but now you have to kind of adjust the coupling depending on the position of the wires. So you can essentially think that each pair of wires form some version of fractionalized excitations, and these can try to hop between wires, and whether they can actually hop or whether the state is gapped, that's the solution. So if you can find that, then you're done. And this is what they did. I won't go into the details because it's very complicated, I think, to explain in 1 minute. But I'll tell you what the result is. So one interesting thing is that the degeneracy, which typically characterizes this Chern insulator phases, is extensive in the system size. So normally if you have a Laughlin state 1/3, you will have 3 states that are degenerate. Here it's extensive in the system size. This is already very different. Also, if you look at the excitations, they're very weird excitations, some that can move along one line. some that can hop one line up to another wire, but then they have to hop back. They can keep hopping, and there are more things like there are other excitations that look more like anyons. You kind of bundle several excitations together, and they move along as a group. And these are more like laughing anyons. So there's a lot of different possibilities that we're still exploring, and also the statistics is a little bit different than the usual laughing case. So this is already an example of some very exotic, possibly unrealistic, but still very cool theorist, I think, result that you can show that there's some phenomenology that you can find by just disordering a little bit some exactly solvable models of strongly correlated phases. Okay, I think that's basically it. I'll mention just a few lines of research that we're doing. So we like disorder also in altermagnets. There's also work by Peru. So if you like altermagnets, you should talk to him. We're doing some tensor network stuff with Sergi. There's some problems in how you represent topological entanglement entropy, and Sergi found a neat solution. As I said, these are superconductors. This is a big line. I also, in the past, just in case there's some experiments in the room, we've worked with experiments on STM or transport simulation in mostly vials and graphene, and also with Fernando, we worked on nonlinear optics, which is a topic that I really like, but I haven't devoted too much time in the last years. But I'm happy to go back now that Fernando is around. And we have some also collaboration with seismologists. Turns out this kind of non-periodic arrays of sites are useful to detect certain types of earthquakes, which is kind of unexpected to me. And there's some people that are crazy enough to have put them in some ice, in some frozen lakes in Finland. It wasn't me, but we're hoping that we can deploy them in Greenland, and there's other places in the world that have used this. So okay, with that, I think I'm gonna stop here, and thank you for your attention.
So thank you very much. Also, time is open for questions, comments. Just a brief thing. So if anyone online wants to make a question, please write that in the chat, and I will read that for our. So the audience, any question, comment? Yes.
How big are these systems that you are solving?
I don't know. How big are these systems? Thousands. I mean, but were you worried of finite size effects, or?
No, to know, just a curiosity. So how many atoms are you taking into account, just to know how do you do the?
I would say you could take like several thousands, yeah. But I mean, you could go larger, but we don't really have to because the gaps are relatively large, and so yeah. There's no, yeah. I mean, in this non-interacting problems, you can get away with relatively small system.
What is the definition of altermagnet in your theory? So usually it's K point and you have spin splitting.
Yeah.
What is in your case?
Yeah, so that's actually the point of our paper, that you can have altermagnets without crystalline symmetries. If you have a local symmetry between orbitals, namely imagine two orbitals that are px and py, and two of them are, then you can kind of essentially say that if you have on all sides, you can rotate these orbitals and flip the spin, and that's a symmetry of your system. I'm not claiming it's realistic, but let's say you can do that. Then when you plot the spectral function of that system, it would look like this. So this is still K-space, just I'm plotting the spectral function, and it'll still be spin split.
This is a tight binding model only.
Yeah.
Tight binding.
How
would the realistic?
We solved we solved the mean field Hamiltonian of some like magnetic interaction that we knew was going to give what we wanted to say. So, I mean, in principle, we have an interaction that does this. Whether you can find a material that has it, that's a different question. But I think the point of this paper was to make the point that you don't need crystalline symmetries to have altermagnets.
What guarantees zero magnetization of the whole system?
Well, every site has two spins. So with our opposite. So that's
So it's zero.
Yeah.
Yeah, my question is how disordered is that system in terms of distance between atoms? I mean, there is a repeated distance over over the space and just a few distances?
Yeah, that's a good question. So realistically, I would say that normally amorphous systems are relatively well grown, let's say. We'll have an interatomic distance that is set by the bonding lengths. So those don't fluctuate that much, even in amorphous systems. They're very peaked to the, let's say, crystalline value. So here, I mean, you can add, I would say there's basically one scale. I mean, I'm not sure if this picture does that, but what we normally do is we relax, you can relax the lattice to have essentially an average nearest neighbor separation, which is more realistic, so to speak. And that makes the hopping dispersion more peaked around some certain value. But you don't have to do that. I mean, I think this is relatively robust because it's a local, in the end, it's a local interaction. So if you're very close to gamma, the wavelength is so large that you're basically averaging over all sites, and you don't really care about like that. Those type of effects matter at the zone boundaries, but not so much at the center. Yeah.
I have many questions, but
This is your hero.
I'm curious about the recent simulations on fractional quantum pole states. And I would like to know a little bit more. Like, these are normally very difficult calculations, especially if you do exact numerical decolorization.
Yes.
So what I want to know, this is what you're doing, or what are you exactly?
Well, that's what we want to do. Yes. We're not the first. So
there's a huge body of.
Right, but with disorder, there's not so many, I think. But
normally they don't do that.
Yeah. So there's a very nice paper by Donna Sheng when she was a student of Haldane. They calculated the many body mobility gap in the fractional chain insulator state in exact diagonalization. And there's a way of doing that by calculating the basically you take so they were in the 1/3 state, and they would take triplets of states and calculate the whole conductivity.
And how large was the system? How large is the system? Because we're typically dealing with 30 sites or something.
Yeah, exactly.
Right?
So that's the typical size.
You can reach the thermodynamics, some conclusions.
I mean, this is a problem that's no matter what you do, right? But I mean, the claim is so. The other thing we want to do is DMRG as well. So this is
still you're severely. You're still severely connected in DMRG.
Yeah, but you can still find fractional chain insulators in DMRG.
With system size.
Yeah, but I mean, in system size in DMRG, you're limited by one direction, but the other one you're essentially in the thermodynamic limit because it's an infinite cylinder. But I mean, finite size effects exist. I mean, I'm not going to deny that, but I guess the state of the art in both DMRG and ED, you would see still it's enough. It's large enough to see well-defined signatures of the fractional state. Whether that survives to the thermodynamic limit,
we can discuss that.
Yeah. But I would say that's the case. But yeah. Okay. Maybe there's some subtleties, but yeah.
Time for a very last question. Anyone? Yes, you.
I have a comment. Cheers. The beautiful inequality that you attributed to me, unfortunately, it was discovered by someone else. By Adolfo, which you cited later.
Yeah. But
we discovered the less beautiful inequality.
Okay, well, I'll update that. It's humble of you too, but I think. Well, I don't know. Okay, yeah. I can give you credit. Nobody has to know.
Okay, anyway, so we are fortunate enough to have Adolfo here. So if any one of you has further questions, just go with me. So thank you very much. And Thomas.
Ya hablaremos.
Sí, no, eso, o sea,
You know Gesa. Okay, if not, I can also talk. Yeah, but it will be, thank you very much. It will be great to have you as a speaker in the colloquium. Yes.
So every time I come here, I go something.
Yeah. But there, you didn't participate in the colloquium series before, right? Because we have the regular seminars, like, but then we also have some kind of
I
colloquium.
didn't know, so but since I'm not here permanent, so I don't know how the series goes.
Yeah. I mean, we can organize a seminar for sure. I don't know how the calendar for the colloquium, because this is Gesa that is considered. Just talk to him, and if
Maybe I should contact earlier if you have a calendar like that. But
yes, schedule before the end of the year. But Gesa may not, because this is it's like one every month. Sorry, one colloquium every 2 months or something like that. So
just I discuss that over the course. So we were the very first to address topology, and I said for sure I told him here several years ago something about with my
Ellos hablan de una infinidad de lo que ellos yo ahí no me queda nunca claro qué relación hay.
This very good result, and also, and unfortunately, I don't like to fight with the referees, so we were unable to pass in physical letters, so I accepted. But it's a highly
Nunca me quedó claro.
When the referees of PRL would say that, I mean, would realize the mistake, right? Yeah. That was
because we were the first to have the idea that some sense topology should be seen in the real space. For several years, I was chasing in the wrong place. So that's the idea I had several years, but I was since we know analytically one case where you have a shared number, which is fully occupied. So we had the exact wave function, and so there is a kind of, let's say, exotic phase factor. They say it's there. Now the phase factor is there because there is a magnetic field, not because of topology, but eventually find where it is.
Okay. Which year is the paper?
2011. Since then, other people have done that. Yeah. And by now, I'm surprised that Adolfo is another former student who worked for that, who is now a young professor of CISA. Made a which has also been announced on the web page of CISA. That is, people use it to say that you have a regular phase transition, you have the Landau theory, you have the critical exponent, you have all of the critical fluctuation, all that stuff. Critical fluctuation, no, because they don't have their own parameter. That is false. The real parameter is our math.
And this is what
yes, and he made the breakthrough, made simulation with the phase transition, and so he showed that it's a phase transition like the others, and there is another parameter.
And which is the name of this?
The paper came out of physical letters a couple of months ago. I was at the time they say. I will send you my fever. I'm going to send you the link to the CISA web page, so you find the popular information.